we will start discussing functions and just reviewing over what we've done with functions before. So let's start by doing some definitions. So first we want to define what a relation is. A relation is just a set of ordered pairs. So if we have, usually we have to do x's and y's. If we have sets of x's and y's together, that's a relation. A function is when we take a relation and it's a relation where for every input there's only one output. Every input, usually that's the x, there is only one output. Usually that's the y. So x is usually what we put into the function, y is what comes out. So a function is where you take that ordered pair and you only have the x's paired up with exactly one y. So we want to test to see if a relation is a function. The first thing we have used was with graphs, we've used the vertical line test. And if you can draw a vertical line and that vertical line hits the graph at 2 or more times, it is not a function. So if you can draw a vertical line that passes through the graph the 2 or more times, it is not a function. So if we look at these two graphs, for instance, as examples, this first one, if I draw a vertical line out here, it only hits it once. But if I draw a vertical line over here, it will hit it even 3 times. So if it hits it 2 or more times, it is not a function. Now this one over here, every time you draw a vertical line, it will only hit it once. So this is a function. It passes the vertical line test. So basically the vertical line test either passes or fails. If it passes and does not hit the graph twice, it is a function. If it does not pass, if it hits it 2 or more times, it is not a function. All right, now let's look at where we do ordered pairs instead to test functions. So what you want to look at with ordered pairs, whether you've got a set of ordered pairs like this, like a relation, or in this way where we do it as a chart, or maybe more as a diagram where this is the input, the x's, this is the y's implied to be inputs and outputs. When you look at this, you want to make sure you check to make sure that the x's are never repeated. So the x's are not repeated. Means it's a function. So in this ordered pair, that would mean the inputs are not repeated to pair with a different output. So here, notice that these 9s, these are the inputs here. So this 9 here, this is a repeat of the x's. So when there's a repeat of the x's, it's not a function. Now this one, this x is paired with that y, this x is paired with that y, this x is paired with this y. The y's are repeated, that's okay. The outputs can be repeated, but the inputs cannot be repeated, so this is a function because the x's are not repeated. And this last one, notice 1 goes with 5, 2 with 6, 3 with 6, and 4 with 7. The 6 is repeated, that's an output, it can be repeated. But in this one, the inputs are never repeated, so this is a function. So that's how you test with more ordered pairs or charts or tables. Now, let's talk about the notation we've used with functions before, just as a review a little bit. So our notation is usually in the form of putting an F with a parentheses and the X afterwards, or other letters. We could use G or H. Usually we'll use some letter, and then X is usually our input, though we could use a different input like say a T, but this is the notation we use. This is read F of X. Okay, so when you look at that notation, it means F of X. F of X equals usually a rule. So usually we'll go F of X equal to some rule. The rule could be, as an example, if we had F of X equal to, let's do 10x plus 3. So as an example, you would have, by the way, this is, if you read this, it's just like saying, y equals this. Y equals 10x plus 3. So if we think of x's and y's, it's the same thing when we have the f of x equals, it's like saying y equals. So when we say f of 7, so here's an example. If we do f of 7, that means substitute 7 in for x and find the y, find the output. So this would be put in 7, you've got 10 times 7 plus the 3, which would be 70 plus 3 would equal 73 for doing that. So just a reminder that this would be our input, this is the output, what comes out of it. That's what functions do. And when I put in 7, I only get out one number. I get 73. I don't get two other numbers. Now, composition of functions are something that we've worked with before briefly. So let's review over a little bit, and we'll build on it this chapter, because we'll do a lot with functions. Functions, Algebra 2 is a lot about functions. So composition of functions, what we usually do is we say the second function is substituted into the first function. So you take the second function, like if we list this, g of x is the second function, we put it into the f function substituted in. It can be listed this way also with a little open circle in the middle. It's not, if it's closed, it's multiplication, but if we have an open circle between the f and the g, that means f of g of x. And same thing here, if we put a parentheses around it, it means the same thing. So these three are this notation for the exact same thing. The way we read this is f of g of x. That's how that notation is read. All right, so let's take a look if we've got this example here. Let's try this first one here. If you do g of f of 7, what you do is ignore the g of x for now and just think about the f of 7. Think about what the inside is, because we're going to put that into the g function. So we're going to first of all find f of 7. That means put it into this function. 7 is the input, so we're going to have 7 squared minus 10 is equal to 49 minus 10, which equals 39. So f of 7 equals 39. So if I'm trying to find g of f of 7, this problem, I'm going to put in where there's f of 7, I'm going to put a 39 instead, because that's what it's equal to. Notice that one goes into the second function. And so I'm going to put this, the 39 is going to go into the g of x. So 39 goes into g of x over here, so it's going to be 2 times 39 plus 5, because that's what my g of x is equal to. So 2 times 39 is equal to 78, plus 5 is equal to 83. So that's what the answer to that example would be. Do the inside part first, substitute it into the first function listed there. Now, when we list this is the same thing. I prefer using this notation. I think this is easier to understand. That means the g of x gets substituted into the f of x. So what I'm going to do is I'm going to take the f function here, and so when I'm doing this, I'm going to take wherever there's an x in this, the input, wherever there's input, I'm going to substitute in for it the g of x. So the x comes out, put it in parentheses, put that g of x in its place. So I'm going to put 2x plus 5 as the input for it. Now I've got to multiply out 2x plus 5 times 2x plus 5 because it's squared. And if you were to double distribute that, multiply out 2x times 2x, 2x times 5, 5 times 2x, etc., you're going to get 4x squared plus 10x, and then the 5 times the 2x is another 10x, and then 5 times 5 is the 25, minus 10. Now we combine like terms, and we get 4x squared plus 20x, and then 25 minus 10 is plus 15 for my answer. So that's what you get when you put those together. So that's composition of functions. Take the second function listed and put it into the first one listed. All right, now, just a reminder of what these families of functions. So again, Algebra 2 is a lot about functions. We're going to build more functions into our course as we go on. The ones that we've already done linear, absolute value, quadratic, polynomial, and rational. The basic graphs of these look like the following. If it's linear, we're going to have a graph looking like this, just a line. Okay, if it's absolute value, we're going to have it look like a V. If it's quadratic, it will look like a parabola somewhere. If it's polynomial, that means we'll do 2 of them. If it's an odd polynomial, remember an odd exponent, it's going to have one going down, the other one going up with it. If it's even, they're both going to be the same direction, just like this one, this quadratic. So I'll put one going down, and whether it goes down or up depends on the leading coefficient, whether it's positive or negative, just as a review. And then lastly, the rational ones. Again, there are many forms of this, but usually we look at some type of asymptote, and we have the graph looking like a type of hyperbola in 2 of the different quadrants. Sometimes it's in different areas, maybe 3 or 4, but it gives sometimes asymptotes, sometimes open or closed dots as part of the graphs. We're going to take some time now to review over what we know about exponents, and then preview and also review a little bit about what we've done with radicals and try to tie them together. So first of all, let's do these rules for exponents. First of all, the product of powers, that's going to be when you have a to the m times a to the n. That's going to equal a to the m plus n, because you've got m factors of a, n factors of a. You bring it together, you have m plus n factors of a, because exponents refer to multiplication. You're going to add those exponents for this one. Quotient of powers is when you divide, so a to the m over a to the n. Division, you're going to take away the factors of a in the denominator, so that means you're going to subtract the exponents. M minus n, because you're taking away factors as the quotient implies. power of a power is when you have a to the m to the n power. So you're going to have a to the m written out n times. You're adding those m's together with the first rule. That also is simpler by just multiplying the m times the n. So bring the n in, multiply it by the m. Now, power of a product, this is where you have to remember that if you're going to have two numbers on the inside here to an exponent, that exponent has to come into each of the terms on the inside. It's got to come into the a, and it's also got to come into the n. So bring the nth power into the a and the n, each of the individual factors on the inside. Negative exponent we've already done, but we want to review this. If you've got it to a to the opposite of m power, you want to recognize that that means you're going to reciprocate it. Make the m a positive, but put it in the denominator. It becomes 1 over a to the m. And this is our new one. This is going to be tying it to our radicals. If you've got an exponent that is a fraction, a to the m over n power. So the fraction isn't outside, that fraction is in the exponent. The denominator of the exponent becomes the index. It becomes nth root of a to the m power. So the numerator becomes the exponent, the denominator becomes the index in the problem. That's new. That's going to be what we build upon in the next few lessons. Now let's do some examples here. Let's try this example where we're going to go ahead and simplify this. The first part doesn't need the parentheses because there's no exponent on the outside of it. But this one, I need to bring that fifth power into each factor. Don't forget the constant. This is where people forget that that fifth power also goes, this is implied to be 2 to the first. 5 times 1 becomes 2 to the fifth. X to the 5 times 5 power, and then y to the 2 times 5 power. So it comes into each of them, and then when there's already an exponent, you multiply by it. So this one I'm going to leave alone for just a moment. 2 to the 5th is equal to 32, x to the 25th power, y to the 10th power. Now when I take this, I'm going to rearrange. I'm going to do 7 times 32 in the front, times x, there's an x to the 4th, an x to the 25th. I'm going to add those exponents. I've got a y to the 3rd, y to the 10th. I'm going to add those exponents because they're the same base. And now I get 7 times 32 gives me 224, x to the 29th power, y to the 13th power is my final answer. So that's how you simplify these two as you bring them together. This one again, I'm going to bring that 2 into each of these terms, 5 squared. This is x to the first. When I multiply the 2 times it, it also gets an x squared. And then y to the 3 times 2, I'm going to go ahead and multiply those two, and I get the 6th power. Remember, it's multiplication when you bring it in. And then times 4, x to the 8th, y to the 10th. X squared is equal to 25, so I'm going to have 25 times 4 in the front. Multiply the numbers, bring those together. X to the 2 plus 8 power here, and then y to the 6 plus 10 power here when I have the same base. So 25 times 4 is 100, x to the 10th, y to the 16th, for a simplified form of that answer. Now let's go back and we're going to do a little review of radicals and how you simplify them, and then we're also going to preview a little bit of some of the what we'll do with different indexes than square roots. So first of all, a reminder that the square root of 144, what that's asking is, it's saying, what do you square to get 144? So that one we might know already to be just 12. Okay, so that one comes out nice and complete. It's a nice, neat integer. Same thing here. We're asking, what do you cube to be 125. Well, 5 cubed is equal to 125, so you can make that equal to a 5. Now, if you wanted to do that on your calculator, what you could do, just as a reminder from what we learned up there, you could take the 125 and make it the 1/3 power. It's 125 to the first power. You put the 3 as the denominator. You could do this on your calculator and you would get that 5 as an answer. Now let's go ahead and do this next one. As a reminder, review a little bit. When we get the square root of a negative, that means you've got to take the I out. You've got to separate this into square root of -1 times square root of 169 plus the square root of 49. Now let's do the square roots. This is equal to an I. This is equal to 13. 13 squared is equal to 169. And the square root of 49 is equal to 7. Now we typically don't leave it in that notation. When we do a complex number, we put the real part first. So you can have a 7 plus, and then you put the imaginary part second. So we put 7 plus 13i when you're writing that out. All right, let's do this last one. Let's review over what we know about function notation and apply it to these functions. And we use these two functions, f of x and g of x, and find these two here and then add them together. So first of all, let's do f of 2. F of 2 means 2 becomes the input in this function. So we have the square root of 3 times 2 minus 4, which is the square root of 6 minus 4. And that's going to be equal to the square root of 2. All right, so for the next part then, what we're going to do is we're going to do g of 12. G of 12 is I go to this function and I put 12 in for it. So I'm going to put 10 times 12 as the input. That gives me the square root of 120. Now this one, what I want to do is I want to go ahead and simplify it. So I'll do that first before I put it in the rest of the problem. What perfect square goes into 120? Well, if you think about it, you got to go through some of your perfect squares. 4 goes into it. So I'm going to make this the square root of 4 times the square root of 30. The square root of 4 is equal to 2. That becomes the coefficient of the square root of 30. So now when I do f of 2 plus g of 12, I'm going to write out what I got for f of 2 is square root of 2. I got this 2 square roots of 30 for my g of 12. And so when I add those together, they're not like terms, and we'll talk more about radical like terms later, but these two radicals are not the same, so I cannot add them together. So that is the final answer. You can't add radicals together unless the radicand are like. So these are not similar terms. So when they're not similar terms, you can't add them together. So what we've done is we've reviewed over some of the exponent rules that we've learned before, and then we've also applied some of that to our radicals, talked about what we knew before about radicals, and then started talking about newer ideas about simplifying radicals.